Outside the bubble, the full intensity of galactic cosmic radiation arrives from every direction, unfiltered and undiminished. And the character of that radiation is what makes interstellar space so much more dangerous than the relatively sheltered environment we inhabit. This matters profoundly for any discussion of interstellar travel or survival beyond the heliosphere. Galactic cosmic rays are not ordinary radiation. They are not like the X-rays you receive during a dental exam or the ultraviolet light that causes sunburn. They are atomic nuclei, primarily protons, but also helium nuclei and heavier ions up to and including iron, that have been stripped of their electrons and accelerated to tremendous energies by astrophysical processes. The primary accelerators are supernova remnant shock waves. When a massive star explodes, the blast wave expands into the surrounding interstellar medium at thousands of kilometers per second. Charged particles caught in this shock wave can bounce back and forth across the shock front, gaining energy with each crossing until they reach velocities approaching the speed of light. Some galactic cosmic ray particles carry energies exceeding 10 to the 18th electron volts, and the most extreme particles ever detected reach 10 to the 20th. For a single subatomic particle, this highest energy is staggering, comparable to the kinetic energy of a fast-moving baseball concentrated into a volume smaller than an atomic nucleus. When these particles strike matter, the results are destructive at the molecular level. A single high-energy cosmic ray nucleus passing through biological tissue ionizes atoms along its track, breaking chemical bonds, damaging DNA, and creating cascades of secondary particles that spread the damage over a wider area. The heavier the nucleus, the greater the ionization damage. Iron nuclei, though they make up only a tiny fraction of the total cosmic ray flux, are particularly devastating because their high charge means they strip electrons from atoms far more aggressively than protons do. NASA classifies these heavy ions as HZE particles, standing for high atomic number and high energy, and considers them one of the most serious radiation hazards for deep space missions. The biological effects of sustained cosmic ray exposure are still not fully understood, in part because no human being has ever been exposed to the full interstellar cosmic ray environment for an extended period. Astronauts aboard the International Space Station receive elevated radiation doses compared to the surface, roughly 72 millisieverts over a 6-month mission, but they still orbit within the protective envelope of Earth's magnetic field. The station's altitude keeps it below the most intense regions of the Van Allen radiation belts, and its orbit never takes it beyond the magnetosphere. Even on a hypothetical mission to Mars, which would take astronauts outside the magnetosphere for roughly 8 to 9 months each way, the total cosmic ray dose is estimated at several hundred millisieverts, enough to meaningfully increase lifetime cancer risk, but probably survivable with careful mission planning. Interstellar space is a different category of problem entirely. Outside the heliosphere, with no magnetic field and no solar wind to attenuate the cosmic ray flux, the radiation dose rate increases substantially. Estimates based on Voyager data and cosmic ray transport models suggest that an unshielded human in interstellar space would receive a radiation dose on the order of several hundred millisieverts per year, possibly higher depending on the local cosmic ray environment. Over a journey lasting decades or centuries, the cumulative dose would be enormous, far exceeding the levels at which cancer, central nervous system damage, cardiovascular disease, and other radiation-induced pathologies become near certainties. And here is where the problem compounds in a way that defies easy engineering solutions. The instinctive response to radiation is to add shielding. Build thicker walls, surround the crew with dense material, block the particles before they reach living tissue. For ordinary radiation, this works. Lead stops gamma rays. A few centimeters of aluminum stop most solar energetic particles, but galactic cosmic rays are not ordinary radiation. The highest energy cosmic ray particles can penetrate meters of solid material. Worse, when a high-energy cosmic ray nucleus strikes a dense shield, it does not simply stop. It undergoes a nuclear reaction with the atoms in the shield material, producing a shower of secondary particles, neutrons, protons, pions, and fragments of nuclei that spray inward toward the very crew the shield was meant to protect. These secondary particles can be more biologically damaging than the original cosmic ray. Studies have shown that thin aluminum shielding, the kind used on the International Space Station, can actually increase the effective radiation dose in interplanetary space compared to having no shielding at all, because the secondary particle production outweighs the primary particle attenuation. Thicker shielding helps, but only up to a point, and the mass required for truly effective cosmic ray shielding is enormous. Materials with low atomic numbers, such as polyethylene or water, perform better than metals because they produce fewer secondary particles, but even these materials would need to be applied in layers many tens of centimeters thick to make a meaningful difference, adding thousands of kilograms to any spacecraft design. It is worth dwelling on this secondary radiation problem because it is one of the most counterintuitive and disturbing aspects of the cosmic ray hazard, and it runs directly against every intuition we have about how shielding should work. On Earth, radiation shielding is straightforward in principle. You put a dense material between yourself and the source of radiation, and the radiation gets absorbed. Lead aprons protect dental patients from X-rays. Concrete walls surround nuclear reactors. Water pools cover spent fuel rods. In each case, the shielding material intercepts the incoming radiation and converts its energy into heat, which dissipates harmlessly. The radiation stops. The person behind the shield is safe. This principle is so reliable, so deeply embedded in our engineering practice, that it feels like a universal law. More shielding equals more protection. In interstellar space, for the highest energy galactic cosmic rays, this principle breaks down. When a galactic cosmic ray nucleus, say an iron traveling at 90% of the speed of light, strikes an aluminum hull plate, it does not gently slow down and stop the way an X-ray photon is absorbed by a lead apron. Instead, the incoming nucleus collides with an aluminum nucleus in the hull, and both nuclei shatter. The iron nucleus breaks apart into a spray of lighter fragments, protons, neutrons, helium nuclei, and pieces of heavier elements. The aluminum nucleus does the same. The collision also generates a cascade of secondary particles that did not exist before the impact. Pions, which quickly decay into muons and gamma rays, neutrons, which are electrically neutral and therefore completely unaffected by magnetic shielding, and a general shower of lower energy but still biologically damaging particles that fans out behind the impact point and penetrates deeper into the spacecraft. This is called a nuclear spallation cascade, and it transforms a single incoming high-energy particle into dozens or hundreds of secondary particles, many of which are more effective at damaging biological tissue than the original cosmic ray would have been. Neutrons are particularly insidious because they carry no electrical charge, which means they cannot be deflected by magnetic fields, and they pass easily through materials that would stop charged particles. When a neutron finally does interact with an atom in human tissue, the result is typically a heavy recoil event that deposits a large amount of energy in a very small volume, exactly the kind of interaction that causes the worst DNA damage. The net effect is paradoxical. A thin shield, say a few centimeters of aluminum, generates a significant number of secondary particles from every cosmic ray it intercepts, while failing to stop the secondaries it creates. The crew behind such a shield can receive a higher total radiation dose than they would with no shield at all, because the spallation products are more numerous and in some cases more harmful than the original cosmic ray flux. A thicker shield reduces this problem because the additional material absorbs some of the secondary particles before they reach the interior, but the improvement is slow and expensive in terms of mass. To achieve a meaningful reduction in dose from a pure aluminum shield, you would need thickness on the order of a meter or more, which translates to tens of thousands of kilograms of shielding mass for even a modest crew habitat. Lower atomic number materials, particularly hydrogen-rich compounds like polyethylene and water, perform better because lighter target nuclei produce fewer and less energetic spallation products. A proton hitting a hydrogen nucleus can only produce a recoil proton, not a shower of heavy fragments. This is why water has been proposed as a shielding material for interstellar habitats, serving the dual purpose of radiation protection and life support resource. But even water shielding needs to be applied in layers of 30 centimeters or more to make a significant difference against the full galactic cosmic ray spectrum, and the mass penalty remains severe for any vehicle that must also accelerate to interstellar velocities. The secondary radiation problem means there is no simple engineering fix for cosmic ray exposure in interstellar space. You cannot just build a thicker wall. The wall fights back. For a short-duration mission to Mars, lasting perhaps 2 to 3 years round trip, the radiation problem is serious but potentially manageable through a combination of modest shielding, mission timing to coincide with solar maximum, when galactic cosmic ray flux is lower, and acceptance of some elevated long-term health risk. For an interstellar mission lasting decades, centuries, or millennia, the problem is qualitatively different. The cumulative exposure grows without limit. There is no solar maximum to time the journey around. There is no possibility of a quick return if the shielding proves insufficient. The cosmic ray environment of interstellar space is a permanent condition, and any vessel traveling through it must either carry shielding massive enough to reduce the dose to acceptable levels for the entire duration of the journey, or accept that its occupants, biological or electronic, will be steadily degraded by radiation damage the entire way. Electronics face their own version of this problem. Cosmic ray particles striking semiconductor components can cause single-event upsets, where a charged particle deposits enough energy in a transistor to flip a memory bit from one state to another. In spacecraft electronics, this manifests as corrupted data, unexpected software behavior, and in severe cases, permanent damage to circuit components. Voyager 1's 2023 communication failure, the corrupted memory chip we discussed earlier, was likely caused by exactly this kind of event. For a probe designed in the 1970s with relatively simple radiation-hardened electronics, this was a recoverable problem. For a more complex interstellar vehicle carrying sophisticated navigation, life support, and communication systems, the chronic bombardment of galactic cosmic rays would represent a continuous reliability threat that compounds over time. Every year in interstellar space is another year of radiation exposure, another year of accumulated damage to circuits, sensors, structural materials, and any biological payload. But cosmic rays are not the only hazard embedded in the interstellar medium. The dust that makes up roughly 1% of the medium by mass presents a completely different category of danger, one that scales not with time but with velocity. Interstellar dust grains are small, typically a fraction of a micrometer across, composed of silicates, carbon compounds, and in some cases, mantles of frozen volatiles. At the densities found in the general interstellar medium, these grains are incredibly sparse. You might encounter only a few per cubic kilometer in typical conditions, and in the low-density hot phase, even fewer. At the speeds of the Voyager spacecraft, 17 kilometers per second, collisions with individual dust grains are minor events. The kinetic energy involved is tiny, and the impacts produce negligible damage. But interstellar travel proposals do not envision traveling at 17 kilometers per second. The whole point of interstellar propulsion concepts is to reach a significant fraction of the speed of light. Breakthrough Starshot, one of the most concrete interstellar proposals currently under development, aims to accelerate gram-scale probes to 20% of the speed of light using ground-based laser arrays. At that velocity, 60,000 kilometers per second, the physics of dust grain collisions changes completely. Kinetic energy scales with the square of velocity. A dust grain that barely registers at 17 kilometers per second becomes a tiny bomb at 60,000 kilometers per second. A grain of interstellar dust weighing 1/1000th of a gram, striking a spacecraft at 20% of the speed of light, releases energy equivalent to roughly the detonation of a small explosive charge. The grain does not bounce off. It vaporizes on impact, along with a portion of the surface it strikes, creating a microscopic crater and a spray of plasma and debris. Individually, these impacts might be survivable for a robust spacecraft, but accumulated over years of travel through even the sparse general interstellar medium, the total number of impacts could amount to significant surface erosion, damage to optical systems, degradation of thermal shielding, and, in worst-case scenarios, penetration of critical structural components. For crewed vessels, which would necessarily be larger and more complex than gram-scale probes, the dust problem is even more acute. Larger cross-sectional areas intercept more grains. Longer journey times mean more total impacts. And the systems at risk: windows, radiators, antenna surfaces, solar panels, are precisely the ones that are most difficult to armor without adding prohibitive mass. Some proposals have suggested forward-mounted shields or deflector systems, but these add mass, complexity, and their own failure modes. The interstellar dust hazard is not a showstopper at low velocities, but it becomes increasingly serious as the desired speed increases, which creates an uncomfortable paradox. Faster travel reduces the time spent in the hostile interstellar environment, but increases the severity of dust collisions. Slower travel reduces collision energy but extends the total exposure time to cosmic radiation and every other cumulative hazard. There is no free variable. Every parameter trades off against another. The magnetic fields of the interstellar medium add another layer of physical reality that any interstellar traveler would have to contend with. The large-scale interstellar magnetic field, measuring roughly 3 to 5 microgauss in our region of the galaxy, is extraordinarily weak by any human standard. It is roughly 100,000 times weaker than Earth's surface magnetic field and billions of times weaker than the field in a medical MRI machine. But its weakness is compensated for by its scale. The interstellar magnetic field extends coherently across parsecs, which is to say, across distances of several light years. It threads through the entire interstellar medium, influencing the motion of every charged particle within it. For a spacecraft carrying no net electrical charge, the interstellar magnetic field is essentially irrelevant as a direct force. But for any propulsion or navigation concept that involves charged particles, plasma interactions, or electromagnetic systems, the background magnetic field becomes a factor that must be accounted for. The magnetic field also governs the propagation of cosmic rays through the medium, scattering them in complex ways that make the local cosmic ray environment variable and difficult to predict in detail. Regions of enhanced magnetic field strength can funnel or focus cosmic rays, creating localized zones of higher radiation intensity. Regions of weaker or more tangled fields may allow cosmic rays to diffuse more freely. The magnetic landscape of the interstellar medium is not uniform, and a traveler moving through it would encounter varying radiation conditions along the route, some better and some worse than the average. Interstellar magnetic fields also carry energy. The magnetic pressure in the interstellar medium is comparable to the thermal pressure of the gas and the pressure exerted by cosmic rays. All three contribute roughly equally to the total pressure balance that determines the structure and dynamics of the medium. This means the magnetic field is not a passive background feature. It actively participates in shaping the interstellar environment, influencing how gas clouds compress and fragment, how shock waves propagate, and how energy is transferred across vast distances. Any model of interstellar conditions that ignores magnetic fields is fundamentally incomplete. Then there is the thermal environment, which presents its own set of challenges. The interstellar medium exists at a wide range of temperatures, from around 10 Kelvin in the coldest molecular clouds to over 1 million Kelvin in the hot ionized phase. But these temperatures are misleading in a way that many people do not immediately grasp. Temperature, in the physics of gases, describes the average kinetic energy of the particles. In the hot ionized medium, individual ions are moving at very high speeds, corresponding to temperatures of 1,000,000 degrees. But because the density is so incredibly low, the total thermal energy per unit volume is negligible. You could pass through million-degree interstellar plasma and not feel any heat at all, because there are so few particles per cubic centimeter that the total energy they could transfer to your spacecraft is vanishingly small. The real thermal problem in interstellar space is not overheating, it is heat loss. In the near vacuum of the interstellar medium, there is no convective or conductive heat transfer. The only way to shed or gain heat is through radiation, and in a region far from any star, the ambient radiation field is extremely faint. Any warm object in interstellar space, whether a spacecraft, a human body, or a piece of equipment, will slowly radiate its heat away into the surrounding emptiness. Without a star nearby to provide a continuous input of energy, maintaining thermal equilibrium requires an onboard power source. For the Voyager spacecraft, the radioisotope thermoelectric generators serve this dual purpose, generating both electricity and waste heat that keeps the spacecraft systems within operating temperature ranges. As those generators fade, the spacecraft will eventually cool to the ambient temperature of interstellar space, a few degrees above absolute zero, and all its systems will cease to function even if the electronics were otherwise intact. For a crewed interstellar vessel, thermal management would be a continuous engineering challenge for the entire duration of the journey. Reactors or other power sources would need to run without interruption to maintain habitable temperatures. Heat rejection systems, typically large radiator panels, would need to function perfectly for decades or centuries. Any failure in the thermal control system, even a partial failure, could cascade into habitability crises within hours or days, and there is no external source of warmth to fall back on, no star to orbit, no atmosphere to trap heat, just the cold, empty medium, patient and indifferent, drawing heat away from any warm body within it at the implacable rate dictated by the Stefan-Boltzmann law. What makes all these hazards so insidious is that none of them, taken individually, is necessarily catastrophic over short timescales. A burst of cosmic radiation does not kill you instantly. A single dust grain impact does not destroy a spacecraft. One cold night does not freeze a habitat. The danger lies in accumulation, in the relentless compounding of small insults over enormous spans of time and distance. Interstellar space does not attack, it erodes, it degrades. It slowly, patiently wears down every system, biological and mechanical, that dares to enter it. A journey of decades through this medium means decades of continuous cosmic ray bombardment, decades of thermal management without resupply, decades of micrometeorite impacts, decades of electronic degradation, decades of radiation damage to structural materials, seals, lubricants, and polymers. Nothing in the interstellar medium is aggressive on a human timescale. Everything in it is lethal on an interstellar one. The interstellar medium is sometimes described as the vacuum of space, but this phrase understates its character. A vacuum implies absence, passivity, the mere lack of something. The interstellar medium is not passive, it is an environment. It has properties, behaviors, and effects. It pushes back, not with walls or storms, but with physics. The cosmic rays do not stop, the cold does not relent, The distance does not shrink. The dust does not clear. Every light year of interstellar medium is functionally identical to the last, presenting the same suite of low-level hazards at the same low-level intensities, and the only thing that changes is the total accumulated dose, the total accumulated damage, and the total accumulated wear. This is an environment that punishes duration, and duration is the one thing that interstellar travel demands in absolute abundance. All of this leads to an uncomfortable realization. The space between stars is not simply far, it is not simply empty. It is a physical environment that creates compounding, escalating obstacles for anything that attempts to cross it. Distance alone would be a challenge enough. But the interstellar medium adds a second layer of difficulty. It fills that distance with a thin, pervasive, inescapable medium that slowly damages everything passing through it. And there is no shortcut through it. The interstellar medium is everywhere between every star in the galaxy. It is the default condition of the Milky Way, and it is far more formidable than its near-invisible thinness would suggest. What remains to be understood is what all of this means when you pull back from the details and look at the galaxy as a whole. Because when you combine the emptiness, the distance, the radiation, and the hostility into a single picture, what emerges is not merely a list of engineering challenges. What emerges is a barrier, perhaps the most fundamental barrier in the natural universe, and one that reshapes how we must think about our place within the galaxy. Step back from the details for a moment. Forget the individual numbers. Forget the density of one atom per cubic centimeter, the cosmic ray flux measurements, and the temperature phases of the interstellar gas. Instead, try to see the galaxy the way it actually is, not as a glittering pinwheel of light, but as a physical structure defined by what lies between the light. The Milky Way contains roughly 400 billion stars. That number sounds like abundance. It sounds like a galaxy overflowing with suns, packed wall to wall with stellar furnaces and their attendant planets and moons. 400 billion is a number so large that it overwhelms intuition, and the natural conclusion is that the galaxy must be a crowded, busy place. But that conclusion is catastrophically wrong, because those 400 billion stars are scattered across a disk, roughly 100,000 light-years in diameter and 1,000 to 2,000 light-years thick, and when you distribute even 400 billion objects across a volume that size, you get something that is overwhelmingly, crushingly empty. The galaxy is not a city of stars. It is a desert with stars in it. Consider the proportions. If you could somehow gather all 400 billion stars in the Milky Way and push them together into a single mass, that mass would occupy an almost vanishingly small fraction of the galaxy's total volume. The rest, the vast and overwhelming majority, is the interstellar medium, the thin, nearly empty, radiation-saturated, magnetically threaded void we have been describing throughout this story. Stars are bright. Stars are important. Stars are where energy is generated, where elements are forged, where planets form, and where life can emerge. But stars are not what the galaxy is made of. The galaxy is made of the space between them. By volume, the interstellar medium is the galaxy. The stars are the exceptions, tiny pockets of dense, luminous matter embedded in an ocean of near-nothingness that stretches in every direction for distances that light itself takes years to cross. This is the perspective shift that changes everything. When you look at the night sky, you see the exceptions. You see the rare concentrations of matter that manage to collapse under gravity, ignite nuclear fusion, and shine. You do not see the medium in which they float. You cannot see it. It is too thin to scatter light in any way your eyes can detect. It is too cold and too diffuse to glow visibly, except in a few specialized wavelengths that require telescopes tuned to radio or infrared frequencies. The interstellar medium is, for all practical purposes, invisible. And because it is invisible, we ignore it. We build our mental model of the galaxy around the things we can see, the stars, and we treat the space between them as though it were simply distance, a number to be overcome by better technology. But it is not simply distance, it is an environment, and that environment has properties that make crossing it one of the most difficult challenges the laws of physics permit. Begin with energy. To move any object across interstellar distances within a time frame shorter than geological epochs, you need velocity. Not the kind of velocity that gets a satellite into orbit or sends a probe to Jupiter. You need a significant fraction of the speed of light. 10% of light speed, roughly 30,000 kilometers per second, is often cited as the minimum practical velocity for interstellar travel, because at that speed, a journey to the nearest star takes approximately 42 years. Slower than that, and you are looking at centuries. Faster than that, and you begin to approach timescales that a single human generation might survive, but the energy costs become staggering. The kinetic energy of a moving object scales with the square of its velocity. This means that reaching 10% of the speed of light requires not 10% of the energy needed to reach light speed, but 1%, which sounds like a discount until you calculate the actual numbers. For a spacecraft with a mass of just 1,000 kilograms, roughly the mass of a small car, accelerating to 10% of the speed of light requires approximately 4.5 times 10 to the 17th joules of energy. That is 450 quadrillion joules. For comparison, the total energy output of all the power plants on Earth in an entire year is roughly 5.8 times 10 to the 20th joules. So, accelerating a single small car-sized object to the minimum practical interstellar speed would consume roughly 1,000th of the entire planet's annual energy production. And that is just the acceleration. Slowing down at the destination requires the same amount of energy again. A round trip doubles it further. Scaling up from a 1,000 kilogram probe to a crewed vessel carrying life support, shielding, supplies, and a crew multiplies the energy requirement by factors of thousands or millions. These are not engineering problems in the conventional sense. Engineering problems have solutions that can be reached through incremental improvements in technology. The energy requirements for interstellar travel are problems of physics, dictated by the mass-energy relationship and the scale of the distances involved. No amount of clever engineering changes the kinetic energy equation. You can choose different propulsion methods: nuclear pulse, fusion, antimatter, laser sail, but every method must ultimately provide the same total energy to achieve the same velocity. The interstellar medium does not create this energy barrier directly, but it is the reason the barrier exists. If stars were separated by millions of kilometers instead of trillions, the energy requirements would be trivial. It is the sheer extent of the interstellar void, light years of almost nothing, that forces the velocity requirement so high and the energy budget so far beyond current capability. Several propulsion concepts have been proposed that attempt to address this challenge, and each one reveals how formidable the barrier truly is. Nuclear pulse propulsion, the concept explored in Project Orion during the 1950s and 60s, envisioned detonating nuclear bombs behind a spacecraft to accelerate it. Theoretical studies suggested that an Orion-type vessel could reach perhaps 3 to 5% of the speed of light using fission bombs, or up to 8 to 10% using thermonuclear devices. These are impressive figures on paper, but they require a spacecraft massing hundreds of thousands of tons, carrying thousands of nuclear weapons, and they still produce a journey time to Alpha Centauri measured in decades to centuries. The concept was never tested at scale, and the political and practical obstacles to launching a nuclear bomb-powered spacecraft from Earth are considerable. Fusion propulsion offers theoretical improvements, using the energy released by fusing hydrogen or helium isotopes to generate thrust, but sustained, controlled fusion remains one of the great unsolved engineering challenges on Earth, let alone in a spacecraft. Even optimistic projections place practical fusion rockets decades in the future, and even if they are realized, the exhaust velocities they could achieve still limit interstellar cruise speeds to a few % of light speed without extraordinary mass ratios. Breakthrough Starshot. The laser sail initiative backed by the late physicist Stephen Hawking and investor Yuri Milner takes a radically different approach. Instead of carrying fuel, the spacecraft is a wafer-scale chip attached to a reflective sail, accelerated by a ground-based laser array to 20% of the speed of light. This concept sidesteps the fuel problem entirely by leaving the energy source on the ground. At 20% of light speed, the probe could reach Alpha Centauri in roughly 20 years. It is the most plausible near-term interstellar concept currently under serious study, and it elegantly solves the propulsion challenge for tiny, gram-scale payloads. But it solves nothing else. A gram-scale probe cannot carry meaningful shielding against cosmic rays or dust impacts at 20% of light speed. It cannot slow down at the destination. It cannot carry instruments much more sophisticated than a simple camera and a communication laser. And it does absolutely nothing for the problem of sending humans or even substantial robotic payloads across interstellar distances. Breakthrough Starshot demonstrates that it might be possible to fling a tiny chip across the interstellar medium. It does not demonstrate that the interstellar medium can be meaningfully crossed by anything resembling a mission of exploration, habitation, or survival. The most common response to the timescale problem of interstellar travel is a concept so deeply embedded in science fiction that many people treat it as an inevitability rather than a hypothesis. The generation ship. The idea is simple in principle. If no single human lifespan is long enough to complete the journey, build a vessel large enough to sustain a self-reproducing population across multiple generations. The crew that launches from the solar system is not the crew that arrives at the destination. Their great-great-great-grandchildren are. The generation ship accepts the interstellar medium's timescale and attempts to outlast it through biology rather than velocity. It is an elegant concept on a whiteboard. It is a nightmare in practice. Consider what a generation ship must actually achieve. It must sustain a human population in complete isolation for centuries, not in the sense that a submarine sustains a crew for months, with resupply missions scheduled and a return to port guaranteed. In the sense of total, irrevocable self-sufficiency, with zero external input for the entire duration of the journey. Every calorie of food must be grown on board. Every liter of water must be recycled with near-perfect efficiency. Every cubic meter of breathable atmosphere must be maintained by closed-loop life support systems that cannot fail catastrophically even once across a span of 300, 500, or 1,000 years. The ship is not a vehicle, it is a world, and it must function as a world with no margin for error over time, scales longer than any human civilization has ever remained stable. Now layer onto this the hazards of the interstellar medium. The cosmic ray flux outside the heliosphere bombards the vessel continuously for the entire journey. Over centuries, the cumulative radiation dose to the hull, the internal systems, and the population itself would be enormous. Shielding helps, but as we have discussed, shielding against galactic cosmic rays requires massive amounts of material, and every kilogram of shielding is a kilogram that must be accelerated to interstellar velocity and decelerated at the destination. A generation ship large enough to sustain a breeding population. Estimates vary but typically start at several thousand people minimum to maintain genetic diversity, would need to be vastly larger and more massive than any structure humanity has ever built in space. The shielding requirements alone could dwarf the mass of the habitable volume. The structural integrity of such a vessel presents its own category of concern. Materials fatigue. Seals degrade. Metals suffer radiation embrittlement over decades of cosmic ray exposure. Polymers break down. Lubricants evaporate or decompose. Every mechanical system on board, every pump, every valve, every bearing, every seal in every airlock and pressure vessel must either last for centuries without maintenance or be replaceable using only the resources carried on board. There is no resupply. There are no spare parts from Earth. If a critical system fails in year 200 of a 500-year journey, the crew must repair it with whatever they have or die. The biological challenges are equally severe. A small, closed population living in a confined environment for centuries would face genetic bottleneck effects, inbreeding risks, and the psychological toll of multi-generational confinement. Social stability over centuries is not guaranteed. Human societies on Earth with vastly greater resources and space routinely undergo revolutions, collapses, famines, and civil conflicts over timescales of mere decades. A generation ship would need to maintain social cohesion, institutional knowledge, technical competence, and a shared sense of purpose across dozens of generations, all while confined to a structure that, however large, would still be incomprehensibly small compared to a planetary surface. The descendants who arrive at the destination would bear no personal connection to the decision to launch. They would have been born into the journey, raised within its walls, and asked to continue a mission conceived by ancestors they never knew. Whether such a population would choose to continue, or would fracture, rebel, or simply lose the technical capacity to operate the ship, is an open and deeply troubling question. The generation ship concept does not solve the problem of the interstellar medium. It absorbs the problem and attempts to endure it through brute persistence. And every hazard the medium presents, radiation, thermal management, dust erosion, material degradation, compounds across the centuries, such a ship would spend in transit. A generation ship is not a shortcut around the barrier. It is a decision to live inside the barrier for the entire crossing, accepting every insult it delivers, for longer than most civilizations have ever lasted. There is one more dimension of the interstellar medium's barrier that we have not yet addressed, and it applies regardless of propulsion method or mission architecture. The interstellar medium is not uniform across the galaxy. Its density, temperature, radiation environment, and magnetic structure vary dramatically depending on where in the Milky Way you happen to be. And for the most part, the variations make things harder, not easier. The galaxy's spiral arms are regions of enhanced density where interstellar gas and dust concentrate, compressed by density waves propagating through the galactic disk. Within the spiral arms, molecular clouds are more common, dust extinction is higher, and the interstellar medium is generally thicker and more structured. Supernova rates are also higher in spiral arms because the denser gas fuels more vigorous star formation, which produces more massive stars that die quickly and violently. This means the cosmic ray production rate is elevated within and near the spiral arms. A vessel passing through a spiral arm region would encounter both higher gas and dust densities and a more intense radiation environment compared to the interarm regions. Between the spiral arms, conditions are somewhat more favorable. Gas densities drop, dust is sparser, and the cosmic ray flux is modestly lower. The interarm regions are the closest thing the galaxy offers to clear corridors between stars, but more favorable is a relative term. The interarm interstellar medium is still a near vacuum, flooded with cosmic radiation. It is still light years wide. It is still devoid of resources and shelter. Calling it easier to cross than a spiral arm is like saying the deep ocean is easier to swim across than a hurricane. Technically true, practically meaningless. Near the galactic center, conditions become dramatically worse. The density of stars, gas, and dust increases sharply. The radiation environment intensifies. Supermassive stellar clusters, energetic nebulae, and the supermassive black hole Sagittarius A star and its associated accretion activity create a radiation-drenched environment that is hostile at scales far exceeding the general interstellar medium. The galactic center is not a place that any known or foreseeable technology could traverse safely, even in principle. In the galactic halo, above and below the plane of the disk, the interstellar medium thins further, but the distances between stars increase enormously. Halo stars are scattered across tens of thousands of light years with vast, empty spaces between them. The medium is thinner, but the journey is longer, and the isolation is even more absolute. There is no direction you can travel in the Milky Way, where the interstellar medium becomes easy. There is no corridor, no gap, no convenient low-density tunnel connecting one star to another. The medium varies, but it never relents. Every route between any two stars in the galaxy passes through light years of structured, radiation-permeated, resource-free void. The barrier is not localized, it is galactic, it is everywhere. Every propulsion concept, no matter how advanced, runs into the same fundamental wall. The interstellar medium is too vast to cross quickly, too empty to harvest for resources along the way, and too hostile to endure for extended periods without enormous investments in shielding, power, and life support. The barrier is not any single one of these factors. The barrier is all of them, simultaneously, compounding across distances that dwarf every other scale of human experience. And there is one more element of the barrier that is easy to overlook, because it is so absolute. Between one star and the next, there is nothing to stop at. On Earth, long journeys are punctuated by waypoints. You can rest, refuel, resupply, and repair at intervals along the route. Even in the age of exploration, when European sailors crossed the Atlantic or rounded the Cape of Good Hope, they could anchor at islands, take on fresh water, patch their hulls, and continue. The ocean was vast and dangerous, but it contained stopping points. The interstellar medium contains none. Between the Sun and Proxima Centauri, there are no planets, no moons, no asteroids of any useful size, no comets, no space stations, no fuel depots, no harbors. There is nothing. Just the medium itself, thin and hostile and featureless, extending without interruption for over 4 light years. A vessel that departs the solar system is committed. There is no turning back without expending the same energy again. There is no coasting into a convenient port. There is no rescue if something breaks. The journey is all or nothing, a crossing of a void that offers no shelter, no resources, and no second chances. This is why the concept of the heliosphere matters so deeply to the story of interstellar space. The heliosphere is not just a scientific curiosity or a boundary on a diagram. It is the last shelter. It is the final protective environment before the full severity of the interstellar medium takes hold. Inside the heliosphere, the solar wind provides a buffer against the worst of the galactic cosmic ray flux. Inside the heliosphere, the sun's magnetic field offers a measure of order and protection. Inside the heliosphere, there is a star nearby, providing energy, warmth, and a gravitational anchor that makes navigation and orbital mechanics possible. The moment you cross the heliopause, all of that ends. The cosmic ray flux jumps. The magnetic environment shifts to the interstellar field, organized on scales of light years rather than astronomical units. The nearest source of energy, the sun, begins to dwindle behind you, its light and warmth fading with the square of the distance until it is just another star in the sky, indistinguishable from the billions of others. Voyager 1 experienced this transition firsthand. Before the crossing, it existed within a bubble maintained by the sun. After the crossing, it existed in the interstellar medium, exposed to conditions that had been the default state of the galaxy for billions of years. The spacecraft did not notice, of course. It is a machine, built to endure a vacuum and radiation. But for any living thing, or any complex system dependent on long-term reliability, the transition from the heliosphere to the interstellar medium is a transition from a sheltered environment to an unsheltered one, and there is no equivalent shelter ahead. The next heliosphere, the astrosphere surrounding Proxima Centauri, does not begin until you are very close to that star, within perhaps 100 astronomical units of it. Between the edge of our heliosphere and the edge of the next, there is nothing but raw interstellar medium for the vast majority of the journey. When you hold all of this in your mind at once, the distance, the emptiness, the radiation, the dust, the cold, the absence of resources, the absence of shelter, the energy requirements, the timescales, the compounding degradation, what emerges is not a list of problems to be solved. What emerges is a picture of the galaxy itself. The Milky Way is a structure in which islands of warmth and light are separated by an ocean that is functionally uncrossable by any technology that currently exists or is likely to exist within the foreseeable future. The interstellar medium is that ocean, and it is not a passive obstacle. It is an active environment with properties specifically hostile to sustained crossing. This does not mean interstellar travel is impossible in principle. Physics does not forbid it. There is no law that prevents a sufficiently advanced civilization from building a vessel capable of enduring the interstellar medium for decades or centuries, and arriving intact at another star. But the resources, the energy, the engineering tolerances, and the sheer duration required are so extreme that they place interstellar travel in a category fundamentally different from any other journey humanity has ever contemplated. Going to the moon took 3 days. Going to Mars might take 8 months. Going to the nearest star, at the fastest speeds any proposed technology can achieve, takes decades. And that is the nearest star. The overwhelming majority of the 400 billion stars in the galaxy are not 4 light-years away. They are hundreds or thousands or tens of thousands of light-years away, separated by proportionally vaster stretches of the same hostile medium. The galaxy is not small and is cluttered with stars. It is enormous and defined by the emptiness between them. This is why the galaxy is silent. This is why, despite hundreds of billions of stars and likely billions of planets, we detect no signals, no probes, no evidence of traffic between stellar systems. The interstellar medium is the answer. Not because other civilizations do not exist, we have no way of knowing that, but because the medium between the stars creates a barrier so formidable that crossing it may be something that very few civilizations ever achieve. And even those that do may find the cost so extreme that they do so only rarely, or on time scales so long that their efforts are invisible to us. The silence of the galaxy is not mysterious when you understand the medium. It is expected. The stars are isolated. They have always been isolated. The interstellar medium ensures it. And yet, in the midst of all this austerity, there is something else. Something that pushes back against the bleakness. Because the interstellar medium is not just a barrier, it is also a record. Every atom of gas drifting between the stars carries information about where it came from and what happened to it. The hydrogen that fills the interstellar void is primordial, forged in the first minutes after the Big Bang. The heavier elements mixed into it, the carbon, the oxygen, the iron, were synthesized inside stars that lived and died billions of years ago, their ashes scattered by supernova explosions into the medium where they now drift. The dust grains are built from those same stellar ashes, assembled atom by atom in the outflows of dying red giants and the expanding shells of supernova remnants. The cosmic rays that flood the medium are accelerated by the shock waves of those same explosions, carrying energy across the galaxy at nearly the speed of light. The interstellar medium is the galaxy's memory. It holds the chemical record of every generation of stars that has ever lived and died in the Milky Way. It contains the raw material from which the next generation of stars and planets will form. It connects the past and the future of the galaxy through a slow, continuous cycle of creation, destruction, and renewal that has been running for over 13 billion years. The same medium that isolates every star from every other star is also the medium that gave birth to all of them. Our own solar system condensed from a cloud of interstellar gas and dust, roughly 4.6 billion years ago. Every atom in the Earth, every molecule in your body, spent millions of years drifting through the interstellar medium before gravity gathered it into the collapsing cloud that became the Sun and its planets. You are made of interstellar material. The calcium in your bones was forged in a star that exploded before the Sun existed, and the atoms of that calcium drifted through the cold, thin, radiation-soaked space between the stars before finding their way into the nebula that became your world. The interstellar medium is not just the barrier that separates you from the rest of the galaxy. It is the substance from which you were made. There is a strange and disquieting beauty in this. The same environment that makes the galaxy unreachable is the environment that made you possible. The vast emptiness that isolates every star system from every other is also the vast reservoir from which every star system was born. The medium is simultaneously the galaxy's greatest obstacle and its most essential feature. Without it, there would be no barrier between the stars, but there would also be no stars to have barriers between. This is the terrifying truth about the space between stars. It is not that it is empty. Calling it empty misses the point entirely. It is that the space between stars is a physical environment, real, structured, and measurable, that creates one of the most formidable natural barriers in the known universe. The distance is the barrier. The emptiness is the barrier. The radiation is the barrier. The cold is the barrier. The absence of shelter is the barrier. The absence of resources is the barrier. Every one of these factors alone would be a serious obstacle. Together, reinforcing and compounding one another across light years of unbroken void, they form a wall that the galaxy has built around every single one of its 400 billion stars. We look up at the night sky and we see light, we see beauty, we see a possibility, and all of that is real. There are worlds out there, orbiting other suns, some of them perhaps teeming with life, perhaps home to civilizations that have looked back at our sun and wondered the same things we wonder about them. But between us and every one of those worlds lies the interstellar medium, not nothing, something vast, something hostile, something patient, and something that does not care whether we ever cross it or not. The medium will still be there in a billion years, thin and cold and saturated with cosmic rays, stretching between stars that have not yet been born. It is the permanent condition of the galaxy. It is the ocean we cannot sail, and perhaps that is the deepest lesson the interstellar medium has to teach us. Not that we are small, though we are, not that the universe is indifferent, though it is, but that the galaxy is structured in a way that makes isolation the default state of every star, every planet, every civilization that has ever existed or ever will. The space between stars is not a problem to be solved. It is a feature of the cosmos. It is how the galaxy is built. The stars shine in solitude, separated by light years of structured emptiness, and the emptiness is not a failure of the universe to fill itself. It is the architecture of the universe itself. We live on one small world orbiting one ordinary star, protected by a thin bubble of solar wind from the full severity of the medium that surrounds us. Beyond that bubble, in every direction, the interstellar void extends outward toward other stars we can see but cannot touch. We are not separated from the rest of the galaxy by nothing. We are separated by something, a medium so vast and so hostile that it may be the single greatest barrier nature has ever constructed. And in the face of that barrier, what we have accomplished is not insignificant. We have sent two small machines beyond the edge of our bubble and into the medium itself.